I will be talking about wind turbines. Most of the talk will be about sort of monitoring, but I'm going to tie in a little bit about commercial aircraft as well. Just what are other things that we can learn about design of commercial aircraft that we can pull over in sort of the wind energy domain. Okay, so I'm going to give just a couple slides. I think most of the people here probably have some or an extensive knowledge of wind energy, but I'll just say a few things about terminology so that, if I'm using some jargon, it kind of makes sense. So this is this Aeolus field station. I'll say a few things about this in a minute. We have a turbine that's just south of our campus. It's a 2.5 megawatt Clipper Liberty turbine. In terms of terminology, there's a Met tower in the background. It's located upstream of the turbine. And then a cell basically houses kind of all the components you see here. So the wind flows past. Basically, you're generating lift on the blades. That causes the rotation of the rotor. And then you're basically turning that mechanical kinetic energy into some electrical energy through some power electronics on the rear of the nacelle. The blades can rotate, and you also have a yaw drive. So most of the talk, I'll probably focus just on the blade rotation. And then there's sort of the power electronics. So you can control the torque that's on the back side of the rotor shaft. So the main name of the game is to capture power, right? So the basic equation that we start from is the power that's available in the wind. It grows with the velocity cubed. And then all the controls is sort of embedded in this kind of power coefficient. Okay, so when you pitch the blades, you're basically changing the angle of attack, the wind conditions, and the rotational speed of the blades. That's all sort of embedded in this one coefficient. But in addition to maximizing the power, you want to minimize loads, and there's sort of operational downtime. And so most of the talk, I'm going to talk on about some monitoring techniques. This picture down here is the blade that's on the turbine that we have south of our campus. So it's a 96 meter is the diameter. So the blades are on the order of, I think, 46 meters. And just to give a scale here, you can see someone in a sort of a worker's vest down here. That's a person standing there. We took a little video here. If he just taps the blade starts vibrating. So on these sort of scale of turbines, there's very large sort of, there's large loads, but they can also have significant vibrational modes. And obviously if you do something wrong, you get massive failures. So what I'm going to talk about is probably I'll spend maybe 5 or 10 minutes just talking about some of the research that's going on at the University of Minnesota. It involves myself, but then some colleagues that I'm working with. So I'll give just sort of high-level snippets here. Then I'll spend maybe 5 or 10 minutes talking about commercial aviation. So as was mentioned, I worked at Honeywell for a number of years. I worked on the Dreamliner, the flight control electronics for that aircraft. Not on the batteries. Those are the parts that are catching fire. So when my mom calls me and asks me what I did wrong, I can tell her I didn't cause it to catch fire. But I'll talk a little bit about what's in this industry and how they make things reliable. And as I said, is there anything that we can use in this industry that might be useful? And then I'll kind of shift over into this monitoring domain. And really, in this area, what we're working on is to try and detect loads on the blades using energy harvesting sensors. And then I'll kind of wrap up at the end. Okay, and ask questions as we go along, and I'll stop and try and answer them. So I'll say just a little bit about this consortium. The consortium was established a couple of years ago through a US DOE grant. This is the turbine that we have. It's a 2.5 megawatt turbine. Here's where our campus is. This is the Mississippi River. The Twin Cities campus there's an east bank and a west bank. So we're kind of situated right along the river. And the field station is down here about 25 miles away. Here's the blade on the ground. So most of the turbine is stock. Here's the Met tower in the background. There's just a few things that are kind of custom. And so in particular, we've got accelerometers and strain gauges at various locations along the blade. And this is supposed to denote high pressure and low pressure side, leading edge and trailing edge. So there are 4 strain gauges at the root. And then at the high and low pressure sides, we have accelerometers at various points along the span. I think this is quarter span here, and then the farthest point out is that 3/4 span. And then strain gauges sort of in between on the high and low pressure side. And then there are also custom strain gauges along the base of the tower. And all this data, the standard data you get from the turbine plus all of these custom sensors, basically it just goes through there's an internet and there's a database that you can access through the web if you want to grab some of this data. Okay. So there's a whole bunch of projects that are sort of centered around this turbine that I'll talk in a little bit about.
What's Aeolus?
Aeolus is the Greek word for wind. So the director of the Aeolus consortium is Greek. So I think that was his, he chose the name. So Greek for wind. So as another collaboration, I'm working with a community college up north. It's Mesabi Range Community and Technical College. They've got a small wind technicians program. It's like a 2-year program where they train people to maintain turbines. And so they purchased this Vestas V27 turbine. Just to give you some scale, here's the Aeolus turbine, 96 meter diameter. The hub height of the rotor is 80 meters. Here's the Vestas turbine, it's 31 meters. The diameter is 27 meters. I know a lot of people here are familiar with the CART at NREL, so to give you some scale, this is 36 meter, 40 meter diameters is sort of the scale. It is a little baby. So you climb. So we went up there and we climbed up here, and they said, okay, now look up at the top of the blade. The blade was pointing straight up, and they said the top of the blade, which we were already up here, it looked like we were pretty high. And incidentally, the U.S. Hockey Hall of Fame is across the street, so they had to point that out to us if you're a hockey fan. They said, okay, look at the top of the blade here, and it seemed extremely high. And they said the top tip of this blade is actually still quite a bit shorter. It's a few meters shorter than just the entire blade of one of these turbines. So you take this blade and you put it here, the dimensions are such that that blade will actually go from ground up beyond the tip of that blade. So the blades on, oops, I think I just turned it off. The blades on these large utility scale turbines, they're enormous. It's about a 3-hour drive for us to get up there. All right. So I'm going to just do kind of some quick snapshots of 6 different projects, and most of the talk I will talk about this last one here. And so if you have any questions about these, I'm going to go through these fairly quickly, but I'd be happy to talk about them in more detail. So the first project, as I mentioned, was this V27 turbine that we're working with up north. So I just have a master's student. Basically, they rewired the entire turbine. They've got a couple compact Rios in the turbine, and I have a student who set it up so that he can design the controller in Simulink, and then it gets ported through the compact Rio. And now he set it up so that he can basically do all this just by FTPing. So the turbine's 3 hours up north. This is a screenshot that he took from his laptop down in the Twin Cities campus, and he can basically watch the turbine with a webcam and start controlling it. At this point, he can just do he can control the rotor speed by pitching the blades. We haven't tried to generate power yet, and so that's kind of the next step. And there are some early references. There was actually a nice RESO report where they were doing some tests on this particular turbine that we're kind of using. And we're kind of thinking of this as just a smaller scale test bed before we kind of test things on the larger scale turbine. That's the future goal. Okay. The next quick topic is sort of wind farm modeling and control. And I know there's been quite a bit of work, by people in this room. Jason and Lucy have done some work here, obviously. What we're trying to do here is something similar. We're working with some people in St. Anthony Falls. They've built a CFD code. This is sort of one quick result to model the flow through the wind farm. And we're also starting to look a little bit at SOFA. These things both require supercomputers to run, so obviously they take some amount of time to run. The St. Anthony Falls code has been they've tried to back validate it against some wind tunnel tests, and they also have some wind farm data that they've tried to validate it against. And so I think we're trying to do 2 things. One, I think the control-oriented modeling is interesting. You're controlling one turbine. What effect does that have on the fluid flow downstream? So the Park models, I think, are maybe the standard model. So we're trying to just validate those or come up with better models than those if possible. And then design controllers that maybe if I derate the lead turbine, can I get more power capture out of the entire farm? I'm going to show just 2 really quick results of this nature. The first result is from the CFD code from St. Anthony Falls. It's a 3 turbine result. So this is normalized power for the first turbine versus time. And there's a transient. Okay, we set some boundary conditions. So really we're looking at the steady state, which is out here. And there are 3 turbines. So 3 simulations. They're basically, the turbines are separated by 5 rotor diameters. And then in the first case, we operate all 3 turbines at the optimal induction factor, which is 0.33. So you operate them optimally. And then in the next 2, you derate the first turbine. You make the first turbine generate less power than it could if it was operating optimally. So if you look at the blue curve, this is the power generated by the first turbine. You notice the blue curve is dropping in each plot. You're generating less power from the first turbine. But if you look at the second turbine, which is the red, it's generating more power as you kind of go along this direction. And then if you look at just the net power sort of in the steady state, you're actually getting more power output by derating the first turbine. So I think there's been several papers of this kind of nature, and this is just a CFD simulation showing this kind of behavior. And so that's something that we're trying to look at. Now, to try and figure out, how should you operate the turbines optimally, the Park model is something that's pretty standard. The Park model would be telling you something about, here's the free stream velocity, how is the downstream velocity affected by the operations of an upstream turbine? And there's a simple relation here where A is the induction factor. And so we were trying to understand, is the Park model appropriate or not? And so this is, again, just a simple CFD showing the downstream distance. There's a turbine at, these are a normalized distance by, I think this is normalized by the rotor diameter. There's a turbine here, and then the blue and red dots are the velocity, either at the hub height or averaged across the rotor plane. And so you see as you go downstream, the free stream velocity is here, it drops at the rotor, you get some lower speed behind the turbine because the turbine's extracted energy, and then it starts recovering. And here was our best fit model with the Park model. And so you can see maybe the fit isn't as accurate as you might want. So the question is, are there better control-oriented models than the Park model? So that's something that we're starting to look at. I know that there's been quite a bit of work here on active power control. I have a student who's just starting to look at this, and so I think there's a lot of interesting things here. I would say we haven't done very much other than he's starting to look at just different gain scheduling techniques. So generally there's a power envelope, and he's trying to figure out, can you just operate seamlessly anywhere within that envelope using gain scheduling techniques? And then the last two things I just quickly want to talk about is, we had Gary Ballas, who's one of my colleagues, and I had a student, Arda Ozdemir. He just graduated recently and went to the MathWorks. He had several papers on using LiDAR for preview control, and again, that's an active area of research. I know quite a bit of work has been done here. And so Arda was looking on this. We have a student who's kind of picked up in his wake, so to speak, and one thing that we were thinking about is, in order to do these sorts of more advanced methods, you need a model, a state space model. And so generally people take these complicated fast models and they linearize them and they get periodic models. And there's a standard technique to get these linearized models, which is the following. You start with a periodic time varying model. This is what you would get by linearizing the fast model. You apply a coordinate transformation, which is based on the fact that the blades are rotating, called the MBC. And you get something that's kind of weakly periodic, and then you just average over one time period and you get an LTI model. So what we were thinking about doing is, you can actually, this multi-blade coordinate transformation, you can actually characterize what are the class of all models that when you apply this transformation, you actually get a linear time invariant model. And so we have a different method which we just say, well, we should take this periodic model and we should somehow optimally approximate it by some model in this set, so that when we apply the MBC, we get an LTI model. And we did this, and it turns out that these two, if you look at the poles or the dynamics, they look the same. But if you look at from input to output, so by that I mean you actually look at the B and C matrices in the state space models, these two approaches give you different dynamics. And for a controls point of view, I'm not sure how this affects the control design, but I think there's some interesting questions about, what is the right LTI approximation here? So I think those are interesting questions.
Why do you want to go to an LTI? Why not stay with a periodic?
You can stay with the periodic. I think the tools are more well developed in the LTI setting. That would be one statement. And I think the other statement is, this multi-blade coordinate transformation, sort of in theory, it should give you an LTI model. And so there's a coordinate transformation, the blades are rotating, you rotate into sort of a fixed frame. That should give you an LTI model. And so if the natural dynamics really are LTI, then why not take advantage of that? So in the helicopter literature, which is where this really started, you would take something which is periodic, and it's really related to the periodicity of this rotation. You apply this transformation, you should get something that's LTI. So I think looking at it in sort of the inertial frame is also, maybe it makes more physical sense.
Well, I was just thinking about your interactions with the tower. They're not going to be LTI.
Mm-hmm. That's probably why you're getting something that's weakly periodic here, I would assume. So when you apply this transformation, you actually don't get something that's LTI. So definitely there's something going on that is not, like, this transformation isn't a perfect transformation. I think that would be my only statement, is I think I at least personally I know more what I would do in the LTI setting than in the periodic setting. I guess I could lift things up, but then, okay, then there's the state dimension issue and so on. I don't know, what are you thinking about?
I like periodic
Okay.
systems. I've even thought about them a little.
Yeah.
So we can talk more later on. I mean, most things that you can do in an LTI setting, periodic setting is almost as good.
Yeah.
And but also, when all the pieces are periodic, I mean, most of the things that you want to do, there is a reasonable version of it. Granted, most toolboxes and all of the fancy stuff that people have worked on is for LTI.
Yeah.
So it doesn't bode well for those of us who like nonlinear things.
Yeah.
So
Okay.
also this would be periodic at a varying frequency when the rotor speed varies, so that might complicate things.
Yeah.
even more.
So it's not truly periodic. The rotor frequency is changing. All right, and so one last sort of quick area it's more, I had a student who's looking at sort of distributed estimation. And the basic idea is if you have a wind farm, it's again related to coordinating the turbines. If the wind flow is coming in a certain direction and you see certain turbines, they're pitching their blades or so on, can you use that information to say something more about the wind flow? So rather than using a LiDAR, can you use the turbines themselves as a sensor? So this is the basic idea, but then we actually got stuck on an even simpler question. And the simpler question was the following. If I give you real-time data from a turbine, can I construct an accurate model of the turbine? Okay, so what he was trying to do was, here's some time series data of the wind. He was doing things at time average to start with, and if he time averages things, he can get stuff that looks accurate. So he's trying to get a CP curve versus tip speed ratio, and that all works out fine. But you'd like to construct this CP curve without using sort of time average data. So you could identify the model just using sort of black box system identification techniques. But we know something about the physics of the model. So he's trying to identify this power curve, which is something telling you about sort of the bulk characteristics of the turbine. And he wasn't successful, and I think we still haven't sorted this out. So finally, he sorted it down to the following question. So I said, forget about the real-time data from the turbine, let's run some simulations. And the simulations he ran were the following. So these are fast simulations where he takes the wind speed, it's spatially uniform, but then it's oscillating at some frequency between 7.9 to 8.1 meters per second. Okay? If it's constant, he'll be able to identify, there's an underlying model in this case that we know what it should be. In the steady state case, he can identify that model. And then if you add just a little bit of oscillations here, there's a green table lookup, which is a little difficult to see. The model that he identifies from this real-time data kind of oscillates around what he thinks it should be the true power coefficient. And if he starts adding even more fluctuations, sort of here's the true power curve, and then the blue curve that he identifies is all over the place. So there's no real result here other than we don't understand how to construct or identify these power curves from real-time data. And so if people have good ideas, I'd definitely like to answer or talk about that. So really the bulk of the talk I want to talk about is this blade health monitoring. Okay? And so what's the motivation for the blade health monitoring? So this is a plot, it's taken by a paper from Falstich and colleagues. Basically it's showing you a bunch of different failures on the turbine, what their failure rate is, so that's sort of the black and gray curves going in this direction, either major or minor failures. And then on the right, when that failure happens, how much downtime is there? Okay, so certain failures, you have a drivetrain failure. It may not happen that often, but if you ruin the gearbox, you have to bring a crane out to site, and you basically have the turbine will be shut down for a couple weeks. Okay, so there are a couple failures that can happen infrequently, but they have sort of long failure times, and then they're kind of average downtime. So here's an example of sort of a damaged gearbox. You just basically pitted the teeth, and then you had to replace the gearbox. All right. So rotor blades are one particular example where they're not the highest rate failure, but they are pretty severe when you fail when the rotor blades crack or they get damaged in some sort. There can be a long downtime. So that's what we're looking at. Now, the cost of wind energy, why do some of this monitoring? Well, it's dominated by the capital costs, and then you've got sort of the maintenance costs as you go on. Okay, so if you can monitor these things, you can do a couple different things. You can do some sort of preventative maintenance. You'll do the maintenance during low winds, or maybe you'll be able to continue operation after failures. So there are many reasons to do monitoring, not just for blades, but for other components. And there's a large literature, and there was a kind of a big competition in the 2011 IFAC where there were lots of different failure modes that people were trying to detect. Okay, and there are lots of different methods. I can do model-based, data-driven, maybe I can have redundant components and so on. So this is where I want to just maybe shift gears for a little bit and talk about aerospace systems, and then maybe try and tie it back to wind energy. Okay. So here's the example that I'm going to talk about. So as I mentioned, this is sort of the aircraft that I worked on, which is the 787. And here's the 777. So I'm mainly going to talk about the 777 just because there's a large literature on the 777. Bob Ye happens to be a senior fellow at Boeing. He was also involved in the 787 design. So I'll talk about the 777, and basically it's kind of similar sort of techniques across the board. The 787 has a lot of sort of nice features. It's the first, I would say, mainly composite airliner, rather than sort of using a metal, fuselage. Honeywell did the flight control electronics. For me, controls was maybe, even I could tell somebody I worked on the flight control, but what I really worked on was fault detection. Okay? The flight controls were designed by Boeing, and Honeywell, in implementing this, was really working on, I would say, the fault detection part. Okay? All right, so here's what things sort of look like on a modern aircraft. You have lots of surfaces. Modern aircraft now are fly-by-wire. There's many reasons to do that. So the pilot is no longer connected directly. There's no cables that connect what the pilot's doing to what's happening on the surfaces. Okay, it's all sort of electronic. There's an interface, and there are many reasons to do that. Reduced weight is sort of a critical driver, but then you can do all sorts of interesting extra performance. So, for example, if you're sitting on the back now, you don't get a bumpy ride because there's gust load alleviation. If you look out the wings when you're on an airplane, you see the wings vibrating. There's gust suppression sort of technology. So if the blade pops up, you can pop up one of the surfaces. That'll cause a force that pushes the blade down. So you can basically take weight out of the wings by doing something that actively damps the vibration. So there's all sorts of new technologies once you sort of eliminate all the cables that you can sort of integrate in. Now, some of the issues are the reliability requirements. They're very strict. So you go to the FAA and you have to convince them that this will fail at a certain rate, and the numbers that people talk about are once every 10 to the 9th hours. Okay, so that's one of the sort of strict requirements. And then there's this no single point of failure requirement. So there can't be any one thing on the plane that'll cause the plane to fail. Okay, and you'll see how these two things show up as I describe the design of the system. So here's how when we teach sort of a classical controls class, we generally think of, oh, there's something I'm trying to control. I get to measure things. I'll measure sort of velocities and angular rates. And then there's actuators on the surfaces. And then there's some computer, the pilot's commanding things to happen, and then there's our standard feedback loop, right? So this is how we teach classical controls. But in reality, it looks something closer to like this, okay? Here's the aircraft. All the sensors have been replicated multiple times because if any sensor fails, you can go to some backup. The actuators are all redundant. There are hydraulic lines, they're triplicated. All the computers are replicated multiple times. There's data buses that are replicated multiple times. The pilot is actually, there's something that's interfaced between the pilot and the computer, because if you lose all the computers, the pilot can still fly the plane through some other loop. And so there's lots of extra complexity. And so if I go to show you, well, this is, if you go look at some of the papers, this is what it kind of looks like in even more detail. There's a whole bunch of sensors over here. Maybe it's a little difficult to see, but there are air data sensors. There are 3 of each. These are inertial sensors. There's 3 or 4 of those. Here are the pilot inputs. They're pulling on a column stick in a Boeing aircraft. Those get sampled multiple times. Triple redundant data buses. All this information goes over to 3 computing boxes. So there are 3 separate computers that could fly the plane. And then here's your little controls piece that we like to design. It's sitting here in the middle. You're kind of doing some signal management at the input and output sides. All 3 computers spit out some commands. It goes back on a data bus. And then this is supposed to represent the rudder, which is on the tail of the actuator. The rudder has 3 separate actuators. So if one of the actuators fails, the other 2 can overpower it. Okay? So there's 3 separate computers. And then if you go and look inside any one of these boxes, it turns out that they've got 3 separate processors from 3 separate manufacturers. Okay? So it's really 9 different processors. And so if you look at this triple redundant, I mentioned kind of two two main requirements that are driving all this complexity. One main complexity or one main driver is that no single failure can cause the plane to break. So that's kind of driving this three separate processors. If Intel's got a problem in their chip line, you don't want that to bring down the plane. Well, now you've got two other sets of processors, right? So you've got this dissimilarity between the components that you're using. And then I mentioned that there's these very low, there are very tight requirements on the probability of failure. Okay, so if there's a random failure, well, that's why you have maybe 3 different sensors, so that if one of the 3 sensors fails for some random reason, the other 2 will kind of take over and outvote it, so to speak. All right, so there's a notion of using dissimilar components, but then also replicating those. And then I like this example. I mean, I learned about this when I was at Honeywell. Aircraft had these sort of ram air turbines, so we're talking about wind energy, so I thought I would throw this in here. If you lose all your engines, okay, so you've probably heard about the pilot who landed the plane in the Hudson, right? You got a bird strike, you lose all the engines. Well, how do you fly the plane? The engines are what are giving all the power for all the computers, and you still need power for the hydraulics to drive the surfaces. So how do you fly the plane if you've lost all the engines? Well, a little air turbine pops out the side, and you generate energy like that. So if you do wind energy, here's another application. A little turbine pops out the side, and you can land in the Hudson, and then I guess you're famous and you retire, and you're done. So I always like this. It sounds kind of cool. So in the aerospace, as I mentioned, these are the kind of the main drivers. No single points of failure, very tight requirements. And the way you do that is lots of hardware redundancy, lots of dissimilar hardware redundancy, meaning buy things from different manufacturers so that you don't get caught with some kind of single design failure. And then lots of this notion of voting. If I've got 3 sensors, I can just compare all 3 and then pick, if only one of them is wrong, I'll pick the right one because 2 out of the 3 will be right. And there's a whole bunch of other things that they do as well that maybe aren't so relevant in our talk. But one thing, like if you're in controls, that is kind of interesting is this notion of equalization. If you've got unstable control laws and you've got 3 computers, let's say one of them is flying the plane and one is just waiting on standby, that backup controller is just kind of sitting there in open loop. It's not really flying the plane. And so if you have backups or spares that are just sitting off to the side and they're unstable control laws, they cause a lot of problems. And the most basic version of this is integral control. Okay, imagine I've got an integral control, and it's not actually flying the plane. It's just sitting on a computer kind of waiting off to the side. It's just running, waiting to run. And this is, in some ways, this is what's happening on a commercial aircraft. You've got a marginally unstable controller and it's just kind of drifting off. And so you have to handle that in some way. So any sort of unstable control laws have to be handled in some special way. Okay. So now let me talk a little bit about the bulk or the main point of this talk, which is the structural health monitoring for blades. Okay, so here's an example from, I think this is from the group in Sandia and a bunch of other collaborators who are working on this. So this is a blade. You can see they've got it censored, they've got it outfitted with sensors all along the blade. And what you'd like to be able to do is, there can be failures in the blade. It's a composite, it can crack and so on. And you'd like to be able to detect whether or not there are these sort of failures. And if you could, detect it before there is sort of a catastrophic failure. And there's lots of challenges. I would say the main challenges I'm going to focus on are, maintaining this wiring for both power and transmitting the data along the blades is, it's not only, maybe technologically it's not a challenge, but it's maybe something people in industry wouldn't want to do. They wouldn't want to have cables running all down the blades. So what we've been trying to think about is can you basically do some sort of sensors along the blades without having extra cabling for the powers, or for the power and for the wireless. So here's sort of the concept that we were thinking about. Imagine you place sensors along the blades. They could be strain sensors or accelerometers, and you have some telemetry, some wireless stuff, so you don't have cables for transmitting the data, and then you have some energy harvester. We've been looking at piezoelectric, but maybe you could look at solar or something else. So you've got something that can generate power at the blades. Now, how are you going to generate this power? In our concept, the blade vibration is actually what's causing the structural loads, but you can actually use that blade vibration to power the sensors as well. Okay, so we're going to actually try and harvest the vibrational energy and use that to power the sensors. And I'm going to describe to you, well, how much energy is there in the vibration of a blade on a utility scale turbine? It turns out that there's not much, so then we came up with a different concept. So there's not enough actually to power strain and accelerometer sensors. So the concept was, well, the harvester itself, treat that as the sensor. The harvester is harvesting vibrational energy, and that strain energy is somehow correlated with damage. So treat the harvester itself as the sensor. And I'll explain more, what the concept is, but that's at the core what it is. Now, the other piece of it is you don't really have a good measurement of what the loading is on the blade. By that, I mean you don't really know what the wind flow is past the blade. You maybe don't have a good structural model. And so we'd like to avoid anything that's model-based. We want to just take data and try and identify failures from the data. And so this is maybe one thing that's just as like a thought from aerospace. Maybe this is the closest thing that we're using. The blades themselves are triple redundant. If you've got these sensors that are transmitting data every so often from each blade, without having a good model, if only one of the three blades has failed, that's, I guess, would be the underlying assumption we're making, you can probably identify the outlier from the three. And so that's really what we're going to try and do. Okay? So what I'm going to describe to you is, first, how much energy is actually available to do this sort of technique. So I'm describing for you, we're going to try and harvest energy from the blades. So I'll describe for you in a utility scale turbine, how much energy could you harvest given current technologies? As I mentioned, it won't be very much. Then I'll describe in a little bit more detail what our health monitoring algorithm is, and then we're doing some experimental work to try and assess the feasibility of this algorithm. Okay, so I'll give just maybe the short intro to doing this sort of energy harvesting. Okay, so the energy that we're going to harvest depends on a bunch of things. It really depends on three things. The first thing is the energy harvester itself. It's going to be a little patch. Okay, it's got certain material properties. It's got a certain efficiency, like what's the efficiency of the energy that you're capturing. It's got a certain amount of volume. Right? It's got an area, and then it's got a width. And then it has some material properties like a Young's modulus, and we're going to normalize it just to make this thing be, kind of have this ratio be unitless. So E naught will just pick something to make all this look normalized. So this design factor will actually have units of millimeters cubed. This is a unitless, the efficiency, and then this quantity here is unitless. Okay. The second thing that we need to know is how much energy is actually available on a wind turbine blade to capture. Okay. So that depends on, again, this is just a constant that we're introducing to make things have the right units. It really depends on the strain amplitude squared and then the frequency of the strain amplitude. So we're going to have to assess that. And then you're going to be able to charge for some amount of time. So you're going to sample, just generate samples for a certain amount of time. That sets the charging time. Okay, so as soon as I tell you these two quantities, the design factor and the available power, you'll be able to start making trade-offs of, if I need to send a certain amount of data, that costs a certain amount of energy, and I'll be able to do it every so often. All right, so here's our experimental setup. It's a little difficult to see, but it's basically a cantilevered beam. We've put strain gauges, and we've got a commercial harvester that we're looking at. There's kind of two harvesters we're looking at. This one is just one that you can go buy for 50 or 100 bucks. This particular harvester, if you go and put in these numbers, the efficiency is actually extremely slow. It's less than 1%. So you only capture about a fraction of a percent of the available power. And then the rest of the numbers, the volume is 117 millimeters cubed. You multiply this all out, and this is a particular design factor for this harvester. One of the colleagues that I'm working with is designing sort of nanotube harvesters. His efficiency is much higher at this point, but he can only do a certain number of layers of the nanotubes, and so he's got a much smaller volume here. And so I'll show you some other number, but his harvesters have a number that's like a half millimeter cubed. Okay, so that's maybe at the more research level. The reason why this efficiency is so low is we're looking at something that's at a very low frequency. Okay, so a turbine generally oscillates at a quarter hertz. So the efficiency of these piezoelectric harvesters is not very good at sort of the sub-hertz level. And then we've got sort of a simple wireless telemetry. This is what it costs to make one transmission. If you just want to send out one piece of data, it's about 92 microjoules. If you want to take a strain measurement and then do a transmission, it costs about 3 times as much, so about 280 microjoules. So these are sort of the experimental numbers that we're dealing with. Here's the overall setup. It's a little difficult to see, but this is the cantilevered beam. There's a little motor that we can just drive the beam back and forth. And so the intent here is you can measure, on our real turbine, we can measure what are the strain levels you see on a blade, and then you could just drive this in a closed loop fashion to duplicate the strain levels in the experiment. So that's what we're going to do. Okay, so we've got numbers for these two things, so I need to tell you in a wind turbine how much energy is actually available. Okay, so what we did was basically we took a FAST model, which is NREL's package for modeling wind turbines. There's a whole bunch of things, wind conditions and so on that you can model, and then there's a whole bunch of outputs. So there's bending moment outputs. They're actually, you can't directly get strain coming out, so we have some just algebraic equations, first principles models that map the bending moments along the blade to what the strain is in the edgewise and flapwise direction. So we do that. And then we did a whole bunch of studies at various turbines in various wind speeds. Okay, so there are 3 different turbines of various sizes. You can kind of see their rated levels here. And then at different wind speeds. So kind of low wind speeds, rated wind speeds, high wind speeds, low and high wind turbulence. So we were just trying to figure out what's the actual amount of energy in these blade vibrations across a variety of different turbines and a variety of different wind conditions. So this part is all just sort of simulation studies. So the sort of thing you would see is the following. Here's time along this axis. This is the blade. So take one blade here. So this is, I think, the 5 megawatt turbine. So it's a 63 meter blade. So that's 63 meters here. And then plot the strain as a function of time. And here's the wind condition. And so you can see the strain as you move along this direction in time. And you could do the same thing in the flapwise direction. Okay? And so one thing we want to do is, okay, well, what location on the blade has the highest strain? Okay, so if you took a slice in the vertical plane along where this blue line is, that's like measure the strain at this red boxed location. You could measure the strain at that location. Okay, so we did that. So pick one location, and this is showing you the strain. This is a simulation study, both in the flapwise and edgewise direction along this blade. And you can see basically it's got some dominant harmonic. So if you take the FFT, you can see there's a pretty dominant spike at one frequency. In this case, it's 0.2 of a hertz. And of course, as you would expect, that is the harmonic frequency of the rotation of the blade. Okay? And the only reason I mentioned this is the strain equation that I gave you for the harvester equation, like the amount of energy that we're harvesting, it presumes a single dominant frequency. So this is just kind of indicating to you that there really is a single dominant frequency, and then we can pull out the amplitude, and then from that we can estimate how much power is available. Okay? And I think this slide is just saying that the power that's available depends on some nominal Young's modulus, which we pick. It depends on the amplitude squared of the strain, and then it depends on the dominant frequency. So basically we did this calculation as a function of the span. What is the power that's available at each point? And here, for example, in the edgewise direction, you see that there's a large amount of power at a certain location. I think this is about a quarter span. And this also maybe lines up with the location where you think there might be most likely the highest point of damage. Okay, so there's where there's the most energy is actually maybe where you want to place the sensors if you're trying to detect damage. So as I mentioned, we did this sort of study in both edgewise and flapwise vibrational directions for 3 different turbines. So there's 3 different turbines here, a whole bunch of different wind conditions. We estimated how much power was available. So these are just showing kind of plots of a whole variety of conditions. And I guess if you are trying to take away some number from this, the larger the turbine, the more energy there is. It makes sense. There's more vibrational motion in the blade. And as you go to higher wind speeds in general, there's more vibrational motion as well. And that probably also makes sense. And so the biggest sort of number on here, just to give you some scale of number, is 60 watts per meter cubed. Okay, so if you're trying to harvest energy in the most favorable conditions, which is high wind speeds, very large turbine, that's about what you're going to get. You can get about 60 watts per meter cubed. So now what does this tell us if we're trying to design some sort of sensor package? What can we say about this? So here's our harvester equation. I've just said at best you're going to get about 60 watts per meter cubed. That's the energy that's available. Okay. So I'm going to do 60 watts per meter cubed, and then 40 and 13 are basically kind of numbers for smaller turbines at less favorable conditions. So I'll make 3 assumptions here based on what we understood from our simulations. Let's say all I'm going to do is send 1 transmission. So that's about 92 microjoules is what it costs. Then you get something that looks like this. Here's the design factor. So you tell me what energy harvester you're going to use. and it's in units of millimeters cubed, somewhere between 11 and 18. And I'll tell you how much time it's going to take you to charge. So the numbers here are in units of minutes. Okay, so if you want to take a measurement, it's going to happen every few minutes. It's a pretty low rate. Now the harvester that we're looking at, this commercial harvester, this is the design factor, about 14 millimeters cubed. So in the most favorable conditions, we can send you a piece of data every 8 minutes, okay? Or every couple minutes. Not very nice if you're trying to do some, if you're going to really measure strain and use this for feedback control. It's pretty much hopeless at this point, unless there's a huge breakthrough in technology. So as I mentioned, most of the energy harvesters are actually focused on very high frequency vibrations, and we're trying to harvest energy at sub-hertz. These things are really not built to be very efficient in that range, so that's the efficiency here is only like a fraction of a percent. And that's where the other component of the research project comes in, is can you design energy harvesters that are actually optimized for low frequencies? Okay, well, let's say you can make it 100 times faster or 100 times more efficient. Well, you're still kind of, I don't know, in the best case scenario, this is 2 minutes, 100, you're basically talking about 1 measurement a second. Maybe you can do something there for controls. Now for health monitoring though, you don't really need necessarily extremely high data rates, right? So the summary here is you really can't use this to power things except for at very low transmission rates. And so what we wanted to understand is, well, can you still do this, some sort of monitoring at very low rates, okay? This is just showing another number. This is Professor Yang has this harvester that's got a higher efficiency, but a much smaller volume. Now you can see the charging times with his harvester as it currently stands is on the order of hours, so that's even worse. So what's the algorithm that we're going to try and investigate? We're going to try and do the following thing. So here's the Liberty turbine. We've taken some strain data. The strain data basically causes this harvester to start accumulating energy. So these are little plots. They're showing time and then the energy that you've harvested. And the concept is the following. Every time you get enough energy to send one pulse of data, so that's on the order of 100 microjoules, you'll send a pulse of data. Okay, so all you're going to get is here's time, and then these are the times when pulses of data come into your health monitoring algorithm. And that's all you get, is you just get pulses of data every few minutes. Okay? Now the concept is that the amount of energy that you're accumulating here is related to the blade strain, and yes, there's all sorts of stuff that's happening at some high rate, but over long periods of time, all that's kind of averaging out. And if there's some damage in the blade, the question is does that damage in the blade show up in sort of long-term trends in how you're harvesting energy? And if it does, the timing of these pulses will be different. Okay? And on this little plot here, there's, this one's supposed to be unhealthy. It's accumulating energy just slightly faster, and over some long period of time, you can hopefully detect that in the timing of these pulses. Okay? So I'm going to describe just a couple initial studies that we've been working on, and then what's our path to actually try and experimentally validate this. So the simulation studies are as follows. We've been taking data either from FAST or the OLOS turbine, so we can actually get strain data because on the research turbine we've got strain gauges all along the blade. So we have no problem getting the strain measurements. We've got some model, so this is the one piece that is being modeled right now. We've got a model for how these strain measurements would get mapped to the accumulated energy. It's a first principles model, except for in the case where if there's damage, we have to have some notion of how the damage affects the strain. Okay, so we've got a very simplified model, and I could speak to that in more detail. This is the part that we really need to validate sort of in the lab. So, but we've got a simplified model that tells us how the strain maps to this accumulated energy. And then once you've got the accumulated energy, as I mentioned, you get these pulses of data. And now you get sort of, if you compare the pulses of data, in this little simulation, 2 of the blades are healthy, one of them's got some damage. It's a crack, let's say, or a delamination in the blade. And you'll just start seeing its time. This is happening on a much faster time scale than would actually happen in reality, just so we can run the simulations. Its time to pulses would start dropping off. So this is supposed to represent time between pulses as a function of the time that you're receiving the pulses. So 2 of the blades are kind of, you're receiving blade pulses at about the same time, but there's random stuff going on here. The blades are all getting slightly different wind loadings and so on. So there's some variability, but over some amount of time, hopefully you can detect these differences. Okay. So what we've done is, as I've mentioned, we've taken some of the data off the clipper turbine, which is, here's sort of the raw strain gauge data from the 3 blades. We do have a model for how that maps to the accumulated energy. And then once you have the accumulated energy, you can map that to signal transmissions. And this is supposed to represent presumably healthy. If this is raw data, the blades presumably haven't been broken yet. And all the timings look roughly the same. Okay.
So on the clipper, you do have wires going to the strain gauges.
We do. And to wire this, though, was actually, I don't have slides of this. It was quite a challenge. We had to do this after the fact. So they had already built the blades. And so we had to install this after the fact. So we had the blades on the ground. One of the graduate students had to build a little robot that crawled deep into the blade. And then when it got to the location you wanted, it had a hydraulic actuator that then slammed the sensor to the inside of the blade, and it had some epoxy. And so he built sort of a one-off sort of robotic arm that could crawl to different parts of the blade. So conceivably you could do that for the install. If it breaks, I think you're kind of out of luck, unless I guess you could have a special custom robotic arm that crawls down the blade as well. And that would be another project I'm sure NSF would be interested in. But that's how it was done. It actually took several months to actually just get the blades installed in that way. So these are wired. And then we took the data, and then in this case, since the blades aren't failed, we had to synthetically inject a fault. And so we synthetically inject a fault in the data, and you can kind of see one of the blades is kind of, the timing between pulses is getting shorter. And so then what we do is we basically compare the ratio of timing between each of the 3 blades. So one of them is the outlier, and that's how we detect it. So it's nothing too special. Okay. I'll tell you in a moment about the experimental work we plan to do, because at this point it's kind of like a hodgepodge of some simulation stuff and some experimental data. So I think basically the point is, I think there's quite a bit of work in the advanced monitoring, and I think especially controls, wind farm level, you can keep reducing the cost of wind energy. The main part of this talk I was focused on this monitoring. I think if you were thinking about this, the main takeaway is that the amount of energy that you can capture is about 60 watts per meter cubed. And really, it's not enough energy to do some sort of real-time control. Okay, that's maybe the takeaway. But what we're thinking about is that this total energy, the energy that you're accumulating, is related to blade damage. And so this is what we're really trying to understand on some level. Can you take that amount of energy, you're getting just very minimal data, can you use that to detect failures in the blades? And so this is what we want to do. There's really 2 pieces that are going. One is this special custom harvester development to take advantage of the fact that the vibrational energy is at low frequency, so it's kind of tuned to that domain. And then the second part is the experimental validation. So as I said, we've got sort of a cantilever beam. We're going to take the blade strain from the turbine. We plan to excite the cantilever beam in the same way that the actual blade would be excited. And then we'll try and we've got a telemetry setup, we'll generate these pulses. And what we intend to do is build sort of different sort of laminates that have kind of failures embedded in them and see if we get different timings between them. So we're going to build different test specimens, some that are healthy, some that have sort of cracks already embedded in them. And that's how we plan to compare it. And then I'd just like to acknowledge, so DOE, and especially this EOLOS consortium, obviously were key for us to do this. And then in Minnesota, we had this Institute on the Environment, and they funded several of the projects that I've talked about here. And then obviously Lucy mentioned the career, which just started for me. All right, I think that's it. Yep.
So when you're collecting the strain gauge data on your blades, do you have a computer that's mounted in the hub that's spinning with the blades, then wirelessly transmitting it to some data collection, or are you using slip rings?
The current turbine, how they've installed it?
Yeah.
That's a good question. I'm actually not sure, but I'm pretty sure I could find out if you want. I don't know how they installed the wiring out to the blades. It's definitely not wireless, so there must be slip rings, but I don't know for certain.
I've heard stories of people crawling out into the cart blades. Like, why can't a person fit into these?
You can, there's a certain, I've never tried to crawl in them, but they've showed me pictures. People, if I went all the way back to the beginning, the Liberty blades, you can crawl out, I think, to about a third or maybe a quarter span.
Okay.
Farther out than that, it just starts narrowing down, and you can't get out there.
Isn't there cross members also?
There's also cross members, yeah. So there's spars and so on throughout it.
Any other questions?
So can we relate the vibration or the blade strength to the like drivetrain damage? Can we relate to that? Is that the purpose of measuring the strength and vibration of the
We weren't trying to correlate it to gearbox damage. I think if you were interested in gearbox damage, a simpler solution would just be put strain gauges on whatever shaft you were trying to understand the loading. I mean, certainly people are interested in gearbox loading and damage to the gearbox, but I think to study that, there's probably an easier path because it's basically all in the nacelle. You don't have the same wiring problems, same issues with sort of maintaining sensors. That's really the issue with the blades, is wiring things and then maintaining sort of all the wiring and cabling out to the blades if something fails.
I guess there is a potential advantage of if you do identify that one of your blades is flexing more and failing and you replace it, it could potentially induce smaller loads on your drivetrain because you're not going to have an imbalanced rotor with
Right.
the loads on it.
Yep. All right, thank you.
Thank you.